Hey guys, what's up? I'm gonna start now. Uh, for those of you online, last time I forgot to share my screen. Please just let me know. I ended up I just edited in all the slides and everything, but for next time, just to not leave you guys in the dark, I'm gonna make sure to share my screen now. And yeah, let's get started. So welcome to last week 6, I think. Today, the whole focus of the whole focus of this week will be to understand how image generation works in AI and build our own image generation pipeline. And I hope to have some really cool results for that by Wednesday. So that will be our final project for this semester. And yeah, let's just get to it. So again, Airtable, but everyone here is in the guild. Let's go straight into it. So image generation in AI. There's actually a lot of generative methods that have been looked into for image generation. There have been GANs, VAEs. Recently, there's been score-based models and flow-based models. Those, I guess, tend more towards like the state of the art right now. We're going to focus primarily on diffusion models. That's like the current industry standard. Have you guys heard of like Stable Diffusion, Midjourney, DALL-E 2? Those were and are diffusion models, with their little quirks and stuff, but we're going to focus on exactly what diffusion is. And yeah, so what are diffusion models? At a high level, they work by starting at random noise and then slowly remove the noise until an image kind of pops up. So this is an illustration of how this works. It has two processes, right? It has the forward diffusion process and then the reverse process. In the forward one, you kind of add noise to an already clear image. And then in its reversal, you train a model to remove this noise. And this is kind of where it gets tricky, right? That's a really high level explanation of that. And it's really intuitive in a sense. You just add noise, take away noise. Now, the whole math behind this adding and taking away noise is pretty dense, honestly. I'm going to go over the most important bits for our schedulers for when we actually code this up. But let's just kind of draw this out in a way. So basically, I mean, you see it there, right? We start off with some image, an image of a house, right? And we have these things that we call time steps. And basically just every time step, every iteration, we jump to a new image. But here we add Gaussian noise. Here's our house, but now we add like a little bit of noise. And then we do that again. This is our forward process. Now we have a bit more noise. Our goal is to reach an image that is literally like pure static. When I say Gaussian noise, you guys are like aware, I guess, of the Gaussian distribution. It is literally our simple bell curve. You could also think of it as the normal distribution. They call that the normal distribution a lot. And the mean here, oh God, so the mean here of the normal distribution, the mean is 0. And a property of the normal distribution is we have like our standard deviations and stuff. There you go. Our sigmas, and I don't know, it's like 34% of our data is like here, 34% is here. So within one standard deviation, it's 68%. And then whatever, 2 standard deviations, I believe it's 95%. Then it's like 97.5, something like that. When we say Gaussian distribution, in general, what we mean is we kind of pick a random value from this distribution. So the mean is 0. So let's say we just pick 68% of the time, we get this value here. Let's say this is kind of like 0.5 or something. And effectively an image, you could see it as like a matrix of pixels, right? So then it has each pixel has like an intensity. Imagine here it's like between an intensity between 0 and 255. Here, let's say it's like 150, the value of this pixel. When we add noise to it, we kind of like, in a way, not add it, like not directly 150 plus 0.5, but we do some kind of formula to kind of change this number up a little bit to maybe 148.2, right? Mathematically, it changes the number. We do this for each pixel. So then you can see kind of how over time, the information kind of gets lost throughout the image. And we add this normal distribution throughout. Normal noise, Gaussian noise, whatever you want to call it. And here we're basically getting some probability. This one doesn't work. That if we think of this as x0, this is our point x0, and our fully noisy image is x of t, and t is like the total amount of time steps that we have. You can see each, whenever we add random noise, we have some probability. Now it should be q. Let me make sure. Yeah. So let's say here this is x of capital T. And let's say here we have 1,000 steps, so t equals 1,000. Right? X0, X1, X whatever. Let's say here is X of like small t. So imagine we're at time step like 500 or something. And this is time step t minus 1, so 499. Each image, in a sense, is kind of the probability of X of t, right? X of t given X of t minus 1. This is for every forward pass, right? This image is the probability that, basically, the probability, since we're randomly adding noise, think of this as a probability, right? Because every step, we might add like a different amount of noise and it's random. So we're saying that this image at X equals t is the probability that it exists given the previous image. That's kind of like a main formula that we have to see here. And then it is simply, like I said, the normal distribution of X of t. And then we have a mean and a variance. Kind of focus on the mean, I guess. Mostly we have one beta of X of 0, and then we have the variance of, beta t given the identity matrix. So this beta, think of it as like the actual amount of noise that we add per step. And let me make sure, t minus 1. This formula basically means this is our X of t. The thing in the first comma, before the first comma, this is the mean. In images, you can largely think of the mean of an image as like its brightness. We want to keep the brightness kind of intact. So like in the Gaussian distribution, we want to keep the change of the mean at 0. And then here we have like our variance. We multiply this by the identity matrix. It's a bunch of convoluted statistics, but intuitively understand that each step is obviously the current step with given the previous steps. This kind of describes how much noise we add per step. The reason we need to keep these variables kind of in balance, the mean and the variance, is because think about, like we talked about in the previous example, pixel value. Let's say we have a pixel value of 254 now. If we add random noise, obviously this value can't be over 255, right? So we have to have some kind of normalization that keeps our values between 0 and 255. So that's basically what the equation is saying at a high level. And then we kind of, do this for every step. So the probability of any time step given X is 0 is like the multiplication of t, and this is like I equals 1 of basically q of x t. given x t x t. Here, what we're basically saying is that for any step t, 0, 1, 2, 3, we can find the actual probability distribution by kind of multiplying the probability from 0 to 1, and then from 1 to 2, and then from 2 to 3. And that's kind of how we get to an x of t with some noise added to that image. And this is our forward process. So the reason we're adding this noise is so that our goal is to get to a fully like noisy image. And our goal basically in Diffusion is to train a model that can predict, right? Here we talked about it. We have x of t given x of t minus 1. We want to do kind of the reverse. We want to find, I'm gonna use p theta. These are like the parameters of the neural network. We want to find p of theta. We want to find x of t minus 1 given x of t. So now we're kind of doing the reverse, right? We want to find the previous noise. We want to approximate the previous noise given our current noise. And that is surprisingly, or maybe not surprisingly, if you have a good grasp of statistics. I personally didn't when I dove into this. So this, you have to understand, this is something we call intractable. It's kind of like too expensive to compute. So we have to find some way to kind of approximate this. And then we have also another problem in doing this. When we want to train a model, let's say, because obviously the strength of the noise here, right, there's more noise here than an early image. So we can't just train the model like in the first step all the time, right? We have to sometimes do it in the middle when there's like a little bit of noise and we have to lower it, or when we have a ton of noise and we want to lower that noise a bit. We want to make sure our model works in all scenarios. And with the equation I gave you, it's a constant multiplication. So that means if we want to get at time, let's say we want to get to time 900, we can't just like teleport there, right? With the equation we were working with, we have to multiply 0 to 1, 1 to 2, 2 to 3. That takes a long time. Now, thankfully, I'm doing this math here because we literally hard code it in our network in what we call the scheduler. We using some like parametrization trick. That beta, which basically defines how much noise we put, if mathematically we reparameterize this, instead of this we use alpha at time step t is equal to 1 minus beta at t. And then we also say that alpha, we call it the alpha bar, is alpha bar t is equivalent to the multiplication. Oh, and I forgot this symbol. This symbol is literally the summation. You know how in a summation you start at 1, you end like, I don't know, at t. And x, this literally means like 1 plus 2 plus 3, right, all the way to plus t. This symbol is literally the same thing, just multiplied, if that makes sense. So, I mean, we have n factorial. Let's say 5 factorial. That's in a way kind of like a reverse, or just this product symbol there. And then we can say that this is the product of all the previous t's. So given that I equals 1 and t, this is just alpha I. We do this reparameterization. Mathematically, we result in this formula using, we find this x of t given the square root of alpha, what was this? Yeah, alpha t at x0, I believe, or xt minus 1. Yeah, xt minus 1, okay. At xt minus 1, we add it to just 1 minus the alpha t at epsilon something. This epsilon is our new descriptor for kind of like the actual noise that we add. This is a, you know, there is some statistical base behind this because when you add multiple Gaussian distributions, it remains a Gaussian distribution. And this kind of helps us literally skip straight to x of t instead of having to multiply each and every time. Right, you kind of see, instead of having to multiply each and every probability, we just kind of multiply this alpha until we get alpha bar. And this, once we start adding, you know, alpha of t minus 1, alpha of t minus 3, whatever, what we end up is with this formula that is, yeah, basically the square root of alpha bar t, yeah, square root of alpha bar t given x of 0 plus, you know, same thing here, alpha bar, and then we have our epsilon. Just think of this formula helps us kind of teleport to a random point with a lot of with a lot of noise in the image. But this is a lot of math, right? Let's jump back into the intuition. And I actually want to talk about how this kind of analogy of how we see these images, right? Here we're seeing it as adding noise, but I want to talk about another kind of way to view what we are doing with diffusion. And I think it's like a very kind of abstract representation, and I guess it represents more what we're truly doing in diffusion. So let's start with talking about what an image is, right? An image, let's talk about like a 2x2 image, and let's say it's grayscale. So we have 4 pixels total. And then each pixel, since we're doing grayscale, only has 256 possible values, 0 to 255 values per pixel. So, you know, this one could be like 12, this one could be 50, 192, and 200. That's kind of our image. And I want you guys to visualize images in this context. Realize if we draw this as a vector, right? 12, 50, 192, and 200. We can describe an image as a point in a 4-dimensional space, like the full image as a point in a 4-dimensional space. In this case, that we have 4 pixels, right? So, you know, I don't know why I even tried to draw it. Let's say it in 2D, right? If we have like a 2-dimensional image, black and white, right? Each kind of image that you can create, it exists in some room, right? Do you guys see that in a way? So now think of a bigger, like an actual image that we use, right? We use, let's say 512 by 512 by 3, right? 512 height, width in pixels times 3 color channels. This is whatever this value is, which I believe it's I've done this like, yeah, it's an easy thing. Imagine this is right, in this case it's 4D. This one is 786,432 dimensions. Literally think of the size of that room. Right, here we're describing an image. Each pixel has like a value. You can describe a certain image as a point in a 786,432 dimensional room. And it's really cool because if you visualize images in this sense, let's imagine we have like a cat, right? We have a picture of a cat. Another picture of a cat in our data set, for example, you know, it might be like looking, I don't know, might be a little offset over here, but the kind of pixel orientation and the values for the most part remain the same in some sense. And then we can also have like a car, whatever. These are the images in our data set. When we map these out to, you know, 786,000 or 4 dimensions, whatever the size of our images are, you start realizing that a specific orientation of pixels kind of create these like mountains in our data distribution. So you could think of the mountains as like, okay, there's a lot of images, there's a lot of pixel orientations that kind of look like a cat here, and then here there's a lot of pixel orientations that look like a car. And you realize that in these orientations of pixels, the vast majority is down here, right? If we think of the y-axis as like a probability, p of x, here 100%, you know, or whatever, 60% of the images have this kind of pixel orientation, they're kind of cats or whatever. Here at 0%, it's because we have like high static images with random pixel distributions. From a top-down view, imagine this is like our 786,000 dimensions. Our actual real images are only kind of here. And imagine that as a mountain. The rest of this is a plane line. Why do I say visualize everything geometrically? When we are adding static to an image, let's say we start here. We start at the cat, right? When we add static to an image, remember, this is like the sea of static random pixel. We kind of just go down step by step. We go down a little hill until we're just in a sea of like Gaussian static. Here, you could imagine here, we start with the pixel, with the image of a cat, and we go down slowly, right? This is us adding image, so, adding noise to the image. At every step, it kind of gets noisier and noisier until the image that we have is closer to this static. Does that make sense? So now think about when we train a model intuitively with this visualization. When we train a model, we're effectively training our diffusion model to do the opposite of that. Now, what does this kind of remind you of? It's very similar to gradient descent, right? You go down the hill. In this case, it's gradient ascent. We want to go up towards wherever our probabilistic gradient is pointing to, I guess. Now, try to like disregard the idea of, you know, typing in a prompt and having the image generate that prompt. Right now, just basically, how do we go from a static image to some image without some prompt, right? We find like kind of the highest point that we can find in this probability distribution. Yeah, so at our point, our model point, again, we're going in the direction of the probabilistic gradient. And this is like some subfield of, like, this whole diffusion theory all came from, I think it's called equilibrium thermodynamics from physics. And there's also a lot of stochastic gradient, differential equation stuff going on, right? Because the slope of a probabilistic mountain is a lot more, stochastic is not as deterministic as the slope of like a normal mountain. But try to visualize everything that we do kind of in this sense. And I think a really cool thought experiment kind of thing that you realize, right? We start from a static point and we climb up towards a mountain until we settle at some pixel distribution that, you know, is like brand new. So that's how we have our brand new image. And think about this, right? We have a mathematical limit to the room that we're in, given the size of our image. So I guess a cool little way to think about this is like, is the model really generating an image, or is it just discovering an image in this space? In a way, kind of. I think both views are correct, but you know, you add a mathematical image, in a way, all the images in the world have already been created, and the model is in a way just finding, you know, like a spot to settle in, remove enough noise where it has like I guess a brand new image that we haven't seen. That's just a cool, I guess, yeah, that's like a cool way to think about that. And I hope that makes sense. Like, so I don't know if you kind of I know it's not images, it's more of like video, but remember like the Will Smith eating the spaghetti? I mean, mathematically, that orientation of pixels have, obviously like exists in that space mathematically. So it kind of just discovered that. Yeah. So I don't know, there's some picture of you out there doing some crazy stuff with like the best quality in the world that you don't even know about. But yeah. Uh, but as you can see, it's like pretty dense mathematically. That's why I try to imagine this in a way. Let me see if I'm missing any equations, because bro, it's like, let me show you actually. Here's a blog, a very famous diffusion blog, and I'd encourage you guys to look this up. Lillian Wang diffusion blog. Lillian Wang, yeah. Here it could explain the math, 20 times better than I can. But just look at how much math goes into the actual like derivations of why we're doing what we're doing. It's a very complex process. Yeah. No, for sure, a lot more. But at a high level, we can definitely view it as such. And I mean, that is mathematically what is going on. There's no reason to really dive into this. Like, we're not mathematicians, right? We need to understand the basis of all of this. And then I guess if you're interested, like, it'd be fun to understand this all the way through. But yeah, this is our diffusion. Let me see if I'm missing anything. Yeah, the reverse diffusion is like, let me erase this. I get ready for like a big formula. The reason I'm writing it down is because we literally code it ourselves, right? But it's a lot better to code like a finished equation than to derive it ourselves. I'm just gonna literally write it from the notes I have, right? So we have, when we're calculating, here's the parameters of our neural network. Yeah, so one step of going backwards is we're using all the same values that we used before, right? What am I doing? Yeah, multiply by x of t minus, here we have our beta again over square root of 1, this alpha bar again. Then we have our noise that is predicted by the model. Ooh, and here, I think, very confusing stuff. I want you guys to also realize that when we want to go backwards in gradient descent, go backwards in diffusion, right? We have this image and we want to go backwards to like a cleaner image. It serves the same purpose to either predict how much noise to remove and to predict what the image was before. It serves the same purpose, right? If we want to get back to one step, obviously one is more computationally easier. Which one is it? Just the noise, not, reconstruct the image each and every step. So ultimately, what we're training our model to do, we want to kind of approximate this value. So our model overall learns to approximate some predicted noise. And the noise is this epsilon. I hope that makes sense. We're training a model to predict the amount of noise that was added from a previous step, and then we remove that instead of like reconstructing. And then the model that actually does this, it's called a UNet. I mean, you see it right here. And I'm gonna go more in depth on what a UNet is. Yeah, the UNet architecture. So let me erase all of this stuff. This is like the most mathematically problematic like meeting we've had. I think this even beats the backpropagation. Because backpropagation, like, yeah, it's a lot of math, but it's just chain rule. You learn that stuff pretty early on when you learn calculus. But this is like, damn. But talking about the UNet architecture, right? This is kind of the model that we use, or the architecture, right? A model is a learned architecture. So this is what we use to learn how much noise is removed from an image. And it's a CNN-based architecture. Originally, it was for like X-ray detection. So like image segmentation, like from like an X-ray, you detect, I guess it would be like a broken bone. I mean, I really don't know how X-rays work, but it would, let's say, I guess if there's a crack in a bone, it would like segment that highlighted. But it's been very useful during diffusion. And we're going to talk about why that is. We're going to go over this. It might look complicated. I just want you guys to know, like, coding this is literally like building like Legos. It's like, you do one block of these, and then you do this whole block, and then it's very like easy to code this. But the unit comprises of 3 parts, and it has one very important inherent quality or aspect that makes it perfect for diffusion and, well, segmentation overall. We have this first half. Let's look at the first half. This first half is what we call like the encoder part, where we encode the image. What is that? Literally like a normal CNN. You encode it to some dimension. Now you have an understanding of, I guess, the features of the image, just like normal CNNs. Here you see that we have like a convolutional layer with ReLU, and then we max pool. The only weird thing about it, I guess, is that we're looking at it going downwards. But if we just like compress this horizontally, it's just a normal CNN. What is very important about this is this part right here. We call these skip connections. So in a way, just think about this. Before we do max pooling, we kind of save that version of the image at every step before max pooling. So before we compress the image, we save that point of the image, we pass it through the bottleneck, and then we upscale the image again using something called a convolutional transpose. That's how you can kind of do the reverse of max pool, go from like an image that's like what the AI sees, it's like stuff that we don't really understand, but it's enough features for it to understand like the depth of the image. And we start upscaling it in a way. So because what we want to do, obviously, we want to like recover the image in a way that we originally had. So in this case, it's like segmentation. I think the example before was, it's always a cat. I'm gonna use a house. We want the model to basically learn that this is a house, so we pass it through, convolutional layer and pooling layers, normal CNN stuff until we reach this bottleneck. But our goal is image segmentation, so we kind of want to, I guess, isolate the house part. So we have to reconstruct our image. The reason we save at each point before the pooling, we like save a copy and we send it over and concatenate it to whatever step we're on here, is because when we work with CNNs, you have to realize that we're making this important trade-off, that we want to increase our understanding of the features of the image. So I guess it'd be like in a house, it'd be like the texture of the walls and stuff like that. We want our model to understand that, but we do that at the expense of spatial information. I mean, you realize that with our convolutions, and then we always pool it, whether it be max pooling or average pooling, we kind of take the maximum value, which might not always be the best value in determining like where our pixels are actually located on the image. So when we're scaling this back up, it is very possible that although our model understands what the image is, the scaled up version is very like off in some way. I don't know. What we do is we save this, each version, and we send them over to we concatenate them as we start scaling it up. So this way we are keeping, as we learn the features of the image, we are keeping the spatial integrity of the image. So now you know that, there's pixels here, pixels here, pixels here, whatever. This forms an image of a house. And when we upscale this, it helps us really maintain the structural information of that image. But now I guess due to whatever happens here, we have a segmentation, like an image segmentation here. So we know that this is the house. In terms of diffusion, you can kind of see this as we go forward in the process so that we learn like the noise that we have given an image. And then when we rescale it, we keep the information of like the shape that we had before. So even if in this image, let's just use the same house example. There's like a bunch of pixels, or sorry, a bunch of noise. We want to kind of figure out how much noise got added. We want to approximate that. By the time we reach this point, it's possible that we have a good answer for the noise, but we don't want to lose the information that we already have, which is like the shape of this house, because that's important as we go backwards. So then when we scale this back up, we have like, we keep the sense of our house, and then we just have like our predicted noise on top of that. And this inherent property, again, skip, that is the worst. Skip connections. Again, we save them and we send them over as we upscale, so that we keep pixel integrity, spatial integrity, while we still learn the actual features of the image. You can kind of edit this however you want, in terms of how many convolutional layers you use, how many max pooling layers you use, how deep you go into the network. For the most part, in some sense, you can literally build this unit by having the picture next to you and just coding up each bit. That's what we'll work on Wednesday. This is the most computationally heavy part for us building. And let's see if I have anything. Yeah. Now let's go through the algorithms in training and inference. How do we train this model? Let me try to translate this math. So, can I erase this? You guys get the vibe of unit. This is a very simple, or not simple because it has a lot of parameters, but the training logic is pretty simple. And you're going to see something like really funny, I guess. So we have x of 0. That is our original image. And we get it from this queue. Think of our data distribution. Literally, we pick out an image, right? T, this just means we randomly select some T, like we talked about. T is one of the time steps. So let's say here we just select a T. And then this epsilon is kind of like the noise that we're adding. And let's look at this right here. Take a gradient descent step on this math, this formula. I'm going to simplify it because for the most part, it remains like this. And then you guys recognize this, right? This is the forward diffusion formula part with the alpha bar and all that stuff. Still don't have this formula memorized, and it's not even that long. So T given with and where we add our epsilon. T. Okay, I'll explain this now. Okay. So this is, I'll do this in blue, or let's change the colors up. I'll do this in red. This is our real noise. This is the amount of actual noise that was at that step or added to that step. And this is what our model predicts. Whenever you see this data, just think of the model parameters. The model has two inputs. It has the image, right? This kind of is our image with the noise. And then this is the time variable that we picked here. Let's say this is at time 300. So we're telling this model, yo, we have this image, it has this, it looks like this, and we're at time 300. Can you kind of estimate how much noise was added in the past step? And yeah, this is our estimation. So let's redraw this or rewrite this formula. We have our true noise minus our predicted noise squared. What is this? This is MSE. Like all this crazy math just to train our model on an MSE. Real noise, predicted noise. It's very convenient because MSE is an easy loss function to optimize on. But yeah, that is kind of our training for the model. And we take a gradient step on that, and then we restart them. We pick a random image at a random time point with random noise. Pass it through, whatever. And then you can also kind of see that our data set becomes kind of not infinite, but it becomes very, it could become very large. We could have 10 images and 1,000 time steps. And then, you know, with 10 images, 1,000 time steps, every time we run this algorithm, we literally pick one random image, let's say image 9, and then we pick a random time step at time 800. And that's just an image with a whole different amount of noise. And we do that again. So even if our data set is only 10 images, it could really become like huge because it's like we're randomly picking a time step with a random amount of noise. We can kind of train our UNet on the same image, just 1,000 different versions of them. And the reason we have to pass the time is because, well, I kind of touched on this before. The noise, naturally, the noise at time 800 is going to be a lot more, and it's going to be a lot more difficult to approximate than the noise at time like 2. At the noise at time 2, the image is literally still intact, and we just have like one random speck there. So that's pretty much our training. Inferencing, you guys recognize this formula. Is that long one that I wrote out before. We're predicting at xt minus 1 given xt. And then we have this. This is, just think of this as like a random jitter, so that what we generate is more unique in a sense. Because otherwise, if we have like a perfect model, it would kind of just go up the hill, and we don't want to end up with the same image we started with. We want to end up with some variation of it. Yeah, so we get a random x of t is just a static image from the Gaussian distribution, and then going backwards, we get some random noise, like extra random noise to add to our past step, and then, yeah, we do that. And it literally looks like noise, next step, little less noise, but now there's a house, and then final step, we have the image that we want to generate. Yeah. That is training and inference for diffusion. So I hope you guys have like a good understanding now of image generation. Obviously I'm recording this, and I know this lecture could be a little on the denser side, but you guys can rewatch the video. This is kind of our image generation, but now we want to add text to it. We don't want to just add or create an image. We want to write what we want. And that is kind of our next thing. How do we, to this whole system, how do we combine text generation? Not text generation, but text conditioning. You guys have like any like predictions, I guess, or any idea of how this could? Think of what we've worked with.
Like text encoders and stuff like that. And encoders, like kind of.
Like clip?
Yeah, clip, but like kind of more.
Literally clips.
Clip. Yeah.
That's our first step in this process. But our first thing, right, we want a text encoder that not only lives in its text encoder world, but lives in the image world as well, and understands the essence of an image. This is clip. We worked on it earlier this semester. Here, this is literally from our project that we implemented earlier this semester. You see how the embeddings get closer for, over each epoch. At a high level, just basically we project the dimensions of an image of a text encoder, right? This sentence, you could put it in one embedding. That kind of explains what that sentence is, the essence of that sentence. We put it in the same dimensionality as the image. And then what we want to do is we want to raise the cosine similarity or normalized dot product between those two embeddings. Raising the normalized dot product basically means that those two embeddings are pointing closer to the same direction or have less of an angle between them. And this kind of teaches our model the essence of things, right? So we know that the embedding for this image is very similar to the embedding of this text, right? So now we have text that translates perfectly to the image world. And what we do with that, we're actually going to talk about another thing we touched on recently, which is attention. If you guys remember, we worked with self-attention for, what was it called? I'm blanking out. GPT, right? We worked with self-attention for GPT at a high level mathematically. We talked about the Apple example. What we have is we have a query, key, and a value. We have she went to the Apple store and got iPhone. And let's say we are on word Apple. Here, that's our query, I guess. That's where we have our query, kind of asking like, yo, what words are very related to me? What words tell me who I am? And the key would be, like iPhone, store, right? So then we perform some dot product between the query and the keys matrix. And the whole idea is that the dot product between the embedding for Apple and the embedding for store is really high. Same thing with Apple and iPhone. Both of those are really high, but maybe Apple and she, right? She doesn't tell Apple much about what it is, I guess, or to, like the word to isn't gonna tell Apple, isn't really gonna give Apple more context on what type of Apple it is, whether it's like, let's try this. Look, whether it's Apple, Apple the phone or Apple the fruit. This was a bad idea. That was a bad idea. Because the logo is the same, but you know what I mean. Right, and then we multiply this with the value matrix. The value matrix basically tells us like, yes, y'all are related. You're good. Like it verifies kind of, in a way you could think of it like that. It verifies, okay, you two are related. Now we're gonna pass our new contextual information about you guys. And then what cross attention is, we touched on it as well before about how the transformer, imagine this is the transformer model, and then it got ripped apart into the encoder only, and then the decoder only, because the original transformer architecture was two things. Right? The whole point was to translate from English to French or German. What cross attention is that we do the same type of operation, but on different data types. In this case, it would be English and French, right? We know just through language, like a word by word translation doesn't result in in a sentence that makes sense in the other language, right? So we still need this kind of attention, but then when we get onto the other data type, we have to cross attention. And then in the case of an image, remember our query is our asker. It's the one asking, and I'm gonna use an example. Let's see if I can up my example game. Let's say a red car, I guess. We have a red car that we want to generate. Oh my God. Yeah. We have a red car that we want to generate. Or just in general, we have a red car in a picture. We have a pixel value in here. Imagine this is 1 pixel. What this pixel does is it asks, like, let's see if I can explain it. It asks like, yo, what words are related to? We're doing this with a pixel now, right? This is why it's called cross attention. We're querying the text key and text value. And then the text, and then the prompt, imagine it's a red car. This pixel wants to know, yo, like, what direction do I go in? Like, am I red or whatever? Thus, the key is like, okay, the car part says red. And then you do the dot product between those two, and you want the similarity, not the similarity, but the relation between the two to be high. Does that make sense at a high level? It's literally the same formula. It's the same formula. This this query times this with the scaling factor times this value. It's the same kind of formula. What we do is we reshape whatever the other data type is to be able to fit this equation, and we just get the same information, like, okay, how related am I here to the words in the prompt? Or if you're a pixel near the tire part, or something, you're kind of asking like, what am I related to within this prompt? And I guess it'd be closer to the car thing. This is at a high level, of course. This is learned through weights and through backpropagation. It's kind of how we get here. But that is the logic behind why we need self-attention. And what we do is we implement these cross-attention blocks throughout our unit. So remember, our unit was here, and then at this level, it's like this and whatever. So it goes through this part, and then it goes back up. We implement cross attention into our unit, like embedding layers. Now, we normally do this mostly to the like lower levels, since there's less information and less actual multiplication to be done. But you could kind of add it, sprinkle it in wherever. This tells us, this basically starts guiding us towards generating an image that is like our prompt. And then the third thing, probably the most difficult concept, to basically what wraps all of this together, is this method that we call classifier free guidance. And we're gonna erase all this again. Start blank again. Classifier free guidance. I explain it here. Think about it as like a knob. It's a value that we put, and using CFG, our model makes 2 predictions. We have the condition, which is what does the noise look like with the prompt and then without the prompt. And then we find the difference between the two to kind of amplify towards what, back to the mountain analogy, what mountain we got to climb. This formula, the way we implement it, it's not with this formula, or very similar to this formula. Here, this is just the noise, right? But we have, think of Z as the noise, and then C is like the prompt. So realize, before, our model was the epsilon predicting the noise given our image. Let's say Z, let's keep using Z here. And then the time step. Here we're using the C for the prompt, for context, whatever. Realize that for the model that we will be building, we want to take care of the time step and take care of the context. So the formula for the model that we'll be working with is we take the image as input, we take a time embedding as input, or the time step, and then we take the context or some prompt. And from there, we do the calculations we need to generate our image. This CFG is really important. I want to tell y'all why. So let's go back to the mountains. If we tell an image to, or if we tell our model to generate an image of a cat, our model tends to not be very confident on what cat, if you don't give it any more detail and you just say image of a cat, how does it know if it's like an orange cat or gray cat, or if it's like a moving cat or a sitting cat? It doesn't. In our model, this has been shown like through different papers. I could guide you guys towards those papers. I'll tell y'all now. But what ends up happening is we end up with an average of what cat means. And normally those are like the really blurry images that you see in AI, like early AI models and stuff like that. If the model isn't confident enough to know, it's given a generic cat and it doesn't know what cat mountain to get on, for example, orange, black, gray, running cat, not cat, whatever. It kind of just settles at an average, which isn't very good. We want it to make a decision. This kind of tells us, right, we do what the model looks like with the prompt. It would end up being like the average thing. It ends up pointing to the model without the prompt. So we make two predictions. Without the prompt, it would end up at something random. And we kind of subtract the two in a way. So we know that we tell the model, okay, from the prompt one, you did this weird cat blob thing. And then without the prompt, you went nowhere. We kind of find the mathematical difference between the two. And then we scale this by some factor. In this case, it's W. I'll show you the one we use in the code. So we scale it up. We're like, okay, the difference between what you thought was a cat and what's like random is like, I don't know. Let's give some number. These numbers aren't, this isn't how it truly works. But just for visualizations, this difference, we can say it's like 9. And then we give it some weight. We're like, okay, that difference, I want you to like go 3 times that. So next time you generate, or whenever you generate an image of a cat, I want you to be 27 times or 27 further from this 0 noise. Now I hope you can see in a way this makes it stronger in its choice of cat. Instead of settling for the average, we go for the separate one. Now in this case, this W is kind of our weight. We use something, we use S. It's literally it's like W minus 1. This is a scale that we use in the code. I think it just like reverses whatever the weight is. And then whenever we do let me show you guys mathematically, right? This formula looks weird. Let me make sure about that W stuff really quickly. Well, we'll figure it out through the algebra. Simple algebra here. We have, get this. Simple algebra here, we have 1. Let's say it's S minus 1. So S minus 1. And then this, let's just say it's our predicted noise minus S minus 1. I guess 0. This is our unconditioned noise. Condition, unconditioned. This is SEC minus S epsilon O plus O. Okay, perfect. So the equation that we use in the code is the noise that it predicts without the prompt plus some scale. We set the scale. We literally set the scale whenever we want an inference, right? Think of this as like this multiplying factor. I did this. No, same thing. So again, we find the separation between the two. We multiply by some scale, and then we add it to the prompt or to the noise that we predict without a prompt. And it kind of separates it further from like this, and it separates it further from just this. And it strengthens its confidence in landing, instead of like finding some middle ground between all of these, it like chooses one. And this is our classifier free guidance. Does that make sense? So we combine those three aspects when we make our model. So summarizing, diffusion works by iteratively denoising an image. And we train a unit to approximate how much noise is removed at each step. We use clip text embeddings and cross-intention to guide the denoising process to generate specific images that we want. And then classifier-free guidance forces the model to generate a stronger image given some text. That's our main pipeline for Wednesday. And there's something I didn't really touch on, and it's going to be part of our build on Wednesday, but it's our use of a VAE. Realize we're building a latent diffusion model, not a diffusion model. Again, let's leave it at really high level because VAE is literally its own science. But basically, the VAE compresses, instead of doing diffusion on the pixel space, which is like, every pixel, we gotta like check the noise for it and whatever. We encode this into some latent space. So some mathematical representation of the image, and we do the diffusion process inside there. It's a lot more efficient. Let's say we go from 512 by 512 by 3. We go to a latent space of 64 by 64 by 3 or by 4, right? It's a lot smaller. It's easier. Think of the room analogy. This is 786,432 dimensions. And this is whatever that is. I think it's 16,000 something. But it's a lot less room for the model to look for the mountain it's supposed to end up on compared to this. It just helps the process be a lot easier. And then once we do the diffusion there, we decode it again to the size of the image that it is. But the logic stays the same, right? The diffusion, just instead of doing the diffusion out here, regular pixel space, we do it inside of a latent space. Much faster, and then we just spit it back out as an image using the decoder. And you see it here, right? We embed the text. This QKV, this is our cross attention, and this is our unit, right? So we start with our image, we encode it into the latent space, and then now we want to find the latent space representation at T, and we want to denoise that. So we pass that through the unit. Look, you can even see the skip connections here, and then you add cross attention at every layer of the unit, and then whatever we spit out, that's what we want generated. We decode it into the pixel space. And that's pretty much the flow that we have. This tells you exactly how the flow of all this works. And oh, I put Monday. But Wednesday, we will code this up, code this monster of a thing, and let's see like the quality of our results. Obviously, it depends on the data set and everything as well. But it should be a very exciting, I guess, project to finish off on. And thank you guys so much for just coming to today's meeting. Again, I know it was a very dense lecture, so I'll be posting the video, and hopefully at least the intuition of diffusion works in your favor and you guys understand it. Also, go through the Lillian Wang blog. Sorry, it is a very cool blog. It contains literally everything you should know. But final meeting. And yeah, and for those of you online, thank you so much for coming today, and I'll see you guys on Wednesday. Bye.